Hello students. So in this class we are going to discuss about moment of inertia. Moment of inertia, which is defined as I, and this moment of inertia is it's not like a vector quantity, although it has magnitude and direction, but it is classified as tensor quantities. It is considered as tensor. Okay, why it has magnitude? It has magnitude, and it has direction based on different axes, because the calculation of moment of inertia is different for different axes. It has magnitude and it depends on axis, but it does not follow, obey vector law. Okay, so let us understand what is this moment of inertia. First of all, what is moment of inertia? Definition. So moment of inertia, moment of inertia is the tendency of a body to resist any change in its state of rotational motion. Just like you have studied about inertia. Inertia is the tendency of the body to resist any change in the linear motion or any change in the velocity. Same manner, moment of inertia is a property due to which body maintains its state of rotational motion, or due to which it resists any change in the state of rotational motion. Change in the state of rotational motion means change in angular velocity. Okay, so change in rotational motion means change in angular velocity. State of rotational motion means angular velocity. Okay, so that's what is moment of inertia. So if your body has very large moment of inertia, that means it's difficult to change its angular velocity. Okay, or if you want to change angular velocity, you have to apply lot of torque. Okay, that we'll see. So that's the concept of moment of inertia. Then how do we calculate moment of inertia? So moment of inertia for a point mass. So let's understand moment of inertia for a point mass. Suppose there is a point mass m. Okay, the mass of this body is m. It's a point mass, and let us consider that there is an axis about which this body can rotate, and this perpendicular distance from the axis is r. What is r here? R is the perpendicular distance of the body from the axis of rotation. Okay, from the axis of rotation, that's the perpendicular distance. So moment of inertia I is defined as m into r square. This is the axis of rotation. Okay, this is how we define for a point mass. Similarly, we can define moment of inertia for system of point mass. Okay, moment of inertia for system of point mass. Moment of inertia for a system of particles. System of particles. So let us say there are so many particles of mass m1, mass m2, mass m3, mass m4 and so on. Let us say till mass mn. And there is an axis about which these particles are rotating. And the distance from the axis are different, of course. R1, R2, R3, R4, R5, like that, Rn. Okay, so R1, R2, R3, R4, Rn. All these are distances. So moment of inertia for the entire, particles, because these are particles. This is one particle, another particle, another particle. All these are particles. So many particles can exist, right? Here, 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 so many. So about this is common axis. Okay, not say that for each particle there will be different type. It's the common axis. Common axis about which it is rotating. Okay. So the moment of inertia for the entire system I net, you can say, is m1 r1 square, m2 r2 square, plus dot 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 plus, you have to keep on doing, mn rn square, like that. Basically you can say that it is summation of mi ri square, where I is going from 1 to n, right? It's just the summation of that. That's quite easy. It's like scalar quantity only, like scalar quantity you are adding. So tensor quantities may be added like scalar quantities only, but if you choose different axes, it will have different calculations. Because r will change, the radius or the perpendicular distance will change, right? Now what about moment of inertia for continuous bodies? Moment of inertia for continuous body. Now a continuous body is made up of particles which are continuously present over the body. So continuous body can be, you know already, right? There can be linear distribution. There can be surface distribution. There can be volume distribution. So basically there can be one-dimensional body, two-dimensional body, three-dimensional body. So these are how the masses are distributed, right? The masses are distributed over length, that is called linear distribution of one-dimensional body. Masses is distributed over surface or a plane, it's a two-dimensional body. And if masses are distributed over a volume or a space, that's a three-dimensional body, right? So for each of these category you can see, but in general I will tell first. Suppose this is a body, let us say some kind of body it is. Okay. Some kind of this object it is. This is a body. And we'll also understand rigid body. What is the concept of rigid body? Okay. So it's a body, let us say, and consider that this matter, and there is axis of rotation. This is the axis, let us say. You consider this as the axis of rotation. So let us say this is a point on the body, and this point on the body is at a distance of, let us say in general this point has a small mass dm, right, and it is at a distance of r. So we'll calculate a small inertia which you say as di. Small inertia is the mass dm into r square, right? The small inertia due to that, and then we can integrate over the entire body to calculate the net inertia about that axis, right? R square into dm I will write. Okay, that's the calculation. That's the calculation that we are going to do for all kind of bodies. And for linear distribution we define linear mass density, surface distribution sigma surface mass density, volume distribution rho volume mass density, right? So all this so for linear or for one dimensional body you can say, or for 1D body you can define lambda is equal to mass by lambda. Okay, this you can write for uniform, and you may also write this as this is mass per unit length. Suppose the length of the body is L, you can write this. Okay, so suppose there is a rod like this, its length is L, mass is M. Mass is uniformly distributed over this body. Okay, so you can define mass per unit length uniform. So, or you may also write this for a small element. If you cut a small element here, this length is dl and its mass is dm. So this ratio dm by dl is still valid for this. So you can calculate from here dm small mass is lambda dm. Okay, like this we can do. Same manner for two-dimensional body also we can do calculation. Two-dimensional body, what example you can take? For two-dimensional body, you can take example of a plate. Plate means like a disc, you can say. It's like a circular disc, let us say. It's a circular disc. Circular disc. Okay, so here in case of a circular disc, again suppose there is some axis about which it is going to rotate. This is the axis. Here we are going to take a small element. That small element mass is dm, and it is present over the area. Which area? That area is dA, right? Area will be dA, isn't it? Very, very small area, dA. So dA here is a small elemental area. Okay, so again here we defined, and suppose the total mass is m and total area is a. So sigma we define as mass by area, and for this small element we can write this is dm by dA, right? That's why the small element mass can be written as sigma dA. Okay, this is how you will calculate the small mass, and then you will be putting in this integration to evaluate the total inertia about this axis. Okay, similarly for three-dimensional body, as I told, mass will be distributed in space for 3D body, right? So if you take example of 3D body, it can be, let us say, like a sphere or something. Sphere means solid sphere, okay, not hollow sphere. Hollow sphere, if you consider, then hollow sphere will be taken not as a three-dimensional body. So let us say that this is a three-dimensional body. Masses are present, and some axis, again you can take some axis. This is the axis of rotation. And if this is the axis of rotation, then again you will define same manner small mass dm. Of course, in all these cases you have to also define the radius. Then only you will be calculating the small inertia, right? Here the small r you will take. Same manner, this small mass at a distance of r, let us say, this r may be changing, and here this is a small volume dv. So here dv refers to small elemental volume, or the volume of element. So you define here rho is total mass by total volume. Okay, suppose the total mass, this object is m, total volume is v, so mass by volume, that is what is density. And if it is a uniform, we can also write this as dm by dv. So that's why you will see the small mass of the element will be rho into dv. This is how we'll calculate, and then after you substitute the small inertia, you will calculate and then integrate it, right? That's the approach. That is the approach of all type of calculations that we are going to do in continuous bodies. A lot of results are there. We will be seeing all those results, right? So let us try to see one or two important results. So take for example a uniform rod. A uniform rod will be like this. Let us say this is a rod, and the mass is distributed over the length. Thickness is negligible, okay, and let us say the length is capital L, the total mass is capital M. We want to find moment of inertia about the axis which is passing through one of the end, and this axis is perpendicular to the length. So this is the axis of rotation. We are considering rotation about this. Now let us calculate. So what is the approach? Because mass is distributed, you have to cut a small element, and let's the length of this element is dx. Okay, the mass of this element is dm. So the small, and the distance from the axis is, let's say this is what is x, perpendicular distance. So the small inertia is the mass m into radius square, radius is x square. Okay, so then the net inertia will be the integration I x square into dm. Now how to write dm here? So first of all you should know lambda, or directly you now write. Now you should write directly what is dm. So dm is equal to lambda dx. Now what is lambda? Lambda is mass by length, m by l, total mass by total length. Okay, so we'll substitute it here. So m by l factor will come out, and you have to do integration x square dx. Next is going from where? Minimum value of x is 0, maximum is l. So x is going from 0 to l. Let us integrate this, and you will get m l x cube by 3, right? X cube by 3, and you have to put the limit 0 to l. So if you are going to solve it, you will see ml l cube by 3 ml square by 3. So this is an important result you have to note. So about the end point of end axis passing through the end of the rod perpendicular, the moment of inertia can be calculated as ml square by 3. Okay, same manner we can calculate about any other axis as well. What will happen if you take axis as the midpoint? Okay, suppose if this rod is rotating about the midpoint, same manner you can do the integration, but only thing, limit you have to change, because the minimum distance and maximum distance will be like this. So you can consider this as x, this axis minus l by 2. and this x will be plus L by 2. Right, so from here you need to consider that, and once you calculate I about this axis, that will come ml square by 2. Okay, so all these results we should note, and lot of results are there which you have to remember in this chapter. This is about moment of inertia calculations for continuous bodies. Okay, so from the standard textbook you can note down all the important results. Now let us move to the two important theorem. With that we'll conclude this topic. So there are two important theorem. One is called parallel axis theorem, parallel axis theorem, and perpendicular axis theorem. So let us first discuss parallel axis theorem. So parallel axis theorem, it is applicable for any type of body, applicable for any type of body. Type of body means it can be one dimensional, two dimensional, three dimensional, any kind of body we can apply parallel axis theorem. What does parallel axis theorem says? Suppose there is an object. Let us say there is an object. Okay, consider this as an object. Okay, now take for example any axis passing through. Let's say the center of mass, first of all locate. Let us say center of mass is here. This is center of mass and this is an axis passing through the center of mass. Now I want to calculate the moment of inertia about the axis which is parallel to the center of mass. This is the axis, this is the axis, and this axis is parallel to the center of mass. Let's write this as I. This is I center of mass, and the distance between the axis, is let's say d. So I about this axis, parallel axis, is I center of mass plus total mass of this object m into d square. Okay, this is how we calculate moment of inertia about the axis which is parallel to center of mass axis. Okay, then we can calculate using this approach. Then let's take example here. Let us consider just now we can verify for the rod we have discussed. Now you can verify whether we are correct or not, right? So let us say that this is a rod. Just now we have calculated moment of inertia passing through this axis is, you can take I center of mass because it is passing through center of mass, isn't it? Which we have already calculated as ml square by 2. And now suppose you want to calculate this about this axis. Remember we have already got this result. This we have already got as ml square by 3. But if you want to check it, and this distance is d, of course this distance d is equal to L by 2 because it's the midpoint. So I will be I center of mass plus md square. Check this, ml square by 2 1 plus m L square by 2. So when you take LCM 2 1, it is ml square plus 3 ml square. So 4 by 12 will become 1 by 3 ml square by 3, right? So you can see that we have already got it. We can verify this, right? Then let us go to the next, perpendicular axis theorem. Perpendicular axis theorem. Perpendicular axis theorem. So in perpendicular axis theorem, it is applicable only for two-dimensional bodies or planar bodies or laminar bodies. These are all the same thing. Okay, planar body, two-dimensional body, laminar bodies. Okay, so now let's understand what it is. So let us consider a disk. Okay, consider that this is a disk. It's a two-dimensional body. Right? This is a disk. Now the disk, this is a circular disk we are taking, circular disk. Here you can take x-axis, this you can take y-axis, this you can take z-axis. All the three are perpendicular to each other, you know that, right? Now here you can clearly see that z-axis and x-axis are in the plane of this body, right? So the body or the disk is present in xz plane, right? And y-axis is like perpendicular to this plane. So moment of inertia about y-axis is equal to moment of inertia about x-axis plus moment of inertia about z-axis. Okay, so try to understand this concept. Do not confuse with symbol x, y, z. That's not the idea. Idea is that x and z is a plane which is, the axis which is present in the plane of the disk, right? So if you know moment of inertia about x and z, you can add both of them. That will give I about the perpendicular axis, which is y-axis here. Okay, that is the idea. We can prove it. It is not very difficult. Let's just quickly prove it. So suppose if you consider a disk like that, and let us say there is a point here, right? You can take this point element dm and its position is x, y, z, because here we have taken this as y-axis, right? This we have taken as x-axis, this we have z-axis. So any point on this will have coordinates, and it is in the x and z, right? So it will have x coordinate as x, let us say. Y coordinate is going to be 0, z coordinate is z, let us say. Correct? So it will have some position. This is origin 0, 0, 0, right? And that's the disk. It's a circular disk. Now if I want to find out moment of inertia of this object, how do I calculate? I need to take about which axis we want. First of all, we want relationship, right? So let us say that you extend this and I also extend this. So if you consider this distance and this distance, what are these distances? So this distance is nothing but x, this distance is nothing but z, isn't it? This distance is z, this distance is x, and this distance from the center origin, that is the distance which you can write as r, which is the position vector of that point. Obviously r square is equal to x square plus z square. Okay, so if you are going to consider moment of inertia about y-axis, you have to take that, of course, integration you have to do, integration of dm into this r square. Similarly, if you want about x-axis, you have to take dm into about x-axis, that distance is z. Inertia, moment of inertia about z-axis, then you have to take integration of dm into x square. So now you see I about y can be written as dm r square, you can write as x square plus z square, and you can open this, so it will become dm x square plus Tm z square. Right, so that is what it is. This is Ix and this is Iz. Right, so we can prove this perpendicular axis theorem. It is only for the planar bodies we can apply that, right? So these are all the theorems that you can understand, and now let us summarize some of the important results. Not all the results, all results you can just go through, but some of the important results for rod already I told. Now take rectangular sheet. Rectangular sheet. If you consider a rectangular sheet whose length is L and width is B, about axis passing through the center. Okay, so this moment of inertia is going to be mass is m, so m by 12 L square plus V square. Okay, then using parallel axis, perpendicular axis, you can calculate about any other axis, but this axis you should remember. This is the axis perpendicular to the plane of this. Okay, it is perpendicular to the plane. Then let's note down for the other one. Of course, if it is a square, then you know it will become m by 6 L square or V square. If you consider that it is like a disc, and ring also you take. First you take ring. If you take ring, so ring means this is how mass will be distributed. Alright. The mass is m and radius is r. So about the axis passing through the center and perpendicular to the ring, or you can say this is the axis of the ring itself. This is the axis of ring. So about this axis, it is just m into r square. Similarly, if you have to calculate about the diameter, there are so many diameters can be there, right? So if you consider a diameter, about the diameter, moment of inertia will be mr square by 2, right? Like that you can calculate. Then next take about the disc. If you consider a circular disc, as I told, we are going to take just circular disc. Take for circular disc, moment of inertia about the axis of the disc. This is the axis of disc, perpendicular, right, the plane. So moment of inertia about this is mr square by 2. M is the mass, r is the radius. Similarly, if you take diameter, any diameter you take, it doesn't matter, because it's a symmetric body. So moment of inertia about the diameter will be mr square by 4. Okay, this you remember. Then next, if you consider a solid cylinder will be like this. Okay. So here also you can consider like about which axis you want to calculate. Solid cylinder. So about the solid cylinder passing through the axis, that is the axis of cylinder, you can see axis of cylinder. Here you can see length is L, radius is r, mass is m. So about the axis, it is just like a disc only, mr square by 2. Okay, but if you have to take about the one of the end and passing like it's a diameter, right? So about this axis, moment of inertia will be, because it's like a rod also, so it is ml square by 3, plus it's like a diameter also, so you have to add this mr square by 4. Okay. Similarly, if you have to take axis passing perpendicular to the rod and from the midpoint or you can say center of mass. So I about this axis will be ml square by 12 plus mr square by, right? So this way you can solve questions on that solid cylinder. Similarly, hollow cylinder, you can note the results on hollow cylinder. Hollow cylinder. Hollow cylinder means it is completely empty. Okay, completely empty. So here about the axis of this cylinder, axis of cylinder, the moment of inertia I will be mr square. M is the mass, R is the radius, L is the length. Again, if you take axis passing through this, it will be here, it will be ml square by, just like a rod you can consider, right? So you have to take this as ml square by 3 plus mr square by 2. Similarly, if you take axis passing through the midpoint or center of mass, here you have to write I as ml square by 12 plus mr square by 2. Okay, like this we can calculate. Then next you take solid sphere. Solid sphere, and you can take next hollow sphere. So if you consider solid sphere, three-dimensional body it is, you can take moment of inertia about diameter. This is a diameter. So moment of inertia about diameter will be 2 by 5 mr square. M is the mass, R is the radius. Okay, and hollow sphere. Hollow means masses are only on the surface. It's like a 2D body. Okay, mass is distributed over the surface. Here also about a diameter, if you want to calculate moment of inertia about diameter, or you can say it is passing through center of mass. So it will be 2 by 3 mr square. And you should note that the moment of inertia for a hollow sphere is more than that of solid, because almost all the masses are present near the axis in case of solid. So if the masses are distributed nearer to the axis, the inertia decreases, and it is away from the axis, inertia increases. So here masses are away from the axis because it is on the surface, right? That's why it is large. 2 by 3, it is 2 by 5. The derivations we are going to skip right now. Okay, so with this we conclude this moment of inertia topic. Then calculations we will be seeing in the PYQs. Thank you for your attention.